Okay, so this is question 10 of the magnetic fields homework booklet. So in question 10, what we start off with this equation. So we've got F equals BQV, and we're told that you can use that to calculate magnetic forces, which we know. We're simply asked to state the condition under which this equation applies, so we just have to say what happens. So the only way you can use this equation is if the magnetic field and the velocity are perpendicular to each other. So that's worth 1 mark. For part 2, we're asked to identify the physical quantities that are represented by the 4 symbols. Basically what they're asking is, what do the symbols in the equation mean? So F is simply the force, B is the magnetic flux density. Magnetic field strength isn't good enough as an answer for that, so it must be flux density. Q is the charge of the particle, and V is the velocity of the particle. You need all 4 of those correct in order to get the 1 mark. So for part B, we're now looking at the path of a charged particle to start off with in an electric field. So we've got this figure. It shows the path that's followed by a stream of positively charged particles, and they've all got the same kinetic energy. So when I see same kinetic energy, I think that they're all travelling at the same speed if they're the same particles. They've got the same mass. As they pass through this region between 2 charged plates, we don't know which one's positive and negative at the minute, then they initially come in horizontally and then they're deflected downwards by the electric field between the plates. So when the electric field's applied, so it's still on, so we've still got a positive and a negative plate, we can correct this path, so the path may be restored to horizontal. In other words, we can move this path back so it becomes a horizontal path again. So there's no overall deflection, and we do that by applying a magnetic field over the same region as the electric field. So basically we put a magnetic field in here which counteracts the effect of the electric field. The magnetic field must be of suitable strength and has to be applied in a particular direction. So first of all, we have to state the direction in which the magnetic field should be applied. Well, again, this is Fleming's left-hand rule. So you take your left hand and you make your normal Fleming's left-hand rule shape. The current, because this is a positive charge, is going from left to right, so you put your second finger from left to right. The force, we want the force to be upwards because these are deflected downwards, so to correct it, the force must be upwards. So you turn your hand so your thumb is pointing up the paper while keeping your second finger pointing along this line. And if you do that, your first finger points into the page. So the direction the magnetic field needs to be applied is into the plane of the paper, which is 1 mark. We're then asked to explain why, when there's no overall deflection, when the magnetic field has been applied and the magnetic field's got the right strength. So we're basically asked to explain why there is no deflection when this happens. So the reason that there is no deflection is because the magnetic force that we've applied upwards is equal to the electric force downwards. So in other words, the resultant force is 0. So if the magnetic force equals the electric force, that's 1 mark. And then we just explain why it means that the path then becomes horizontal. And so we say the resultant vertical force is 0 because these two things act in opposite directions. And so therefore we get 2 marks. 1 mark for that, 1 mark for the second point. In part 3, we're then given some more information. So this stream of ions passes between the plates at a velocity of 1.7 times 10 to the 5 meters per second. The separation between the plates is 65 millimeters, and we know the potential difference across them is 48 volts. We're asked to calculate the value of B, the magnetic flux density, so that there's no overall deflection of the ions, and we need to also state the appropriate unit. So lots of people missed that part of the question, so we're going to make sure we put the right unit in. So if we draw a little diagram, what we know is that the electric force downwards, which is equal to EQ, E is the electric field strength, and Q is the charge of our particle, is equal to BQV, the magnetic flux density, multiplied by the charge of the particle, multiplied by the velocity. So these two are equal to each other. And if we rearrange this, the Q's cancel, so we get the magnetic flux density is equal to the electric field divided by the velocity. Now we know the velocity in the question, that's here. What we don't know is the electric field strength, but we can work that out because we know that for a uniform field, which this is because it's between 2 parallel plates, the electric field is equal to the potential difference divided by the separation between the plates. The potential difference is 48 volts, separation is 65 millimeters, so 65 times 10 to the minus 3 meters. So the electric field strength is 738.46 volts per meter. We now take this equation and we put it into this equation with the correct velocity, that looks like this. We do it on our calculator and we get 4.3 times 10 to the minus 3. Now don't forget, we're asked to state the appropriate unit, so the unit of magnetic flux density is the Tesla. So in terms of your 4 marks, basically you get 1 mark for identifying how you calculate B, you get another mark for identifying the actual value of the electric field strength, you get 1 mark for the correct answer, and then your 4th mark is for the unit. The final part of this question is to explain what would happen to the ions if we, instead of using the ions that we did use, we used ions that had a higher velocity. When they pass between the plates, when the conditions have already been established. So in other words, the electric field and the magnetic field are fixed. So we use a magnetic field of the value we've just worked out, and the potential difference across the plates doesn't change. We simply put in ions that now have a higher velocity, and we would ask to explain what's going to happen. So we need to say what's going to happen and why. So what's going to happen? Well, the ions would be deflected upwards, so the path wouldn't be horizontal anymore. Why? Well, the electrostatic force, which acts downwards, is unchanged because velocity doesn't have any effect upon electrostatic force. But the magnetic force does increase because we know that force is equal to BQV. So if we increase velocity, we increase the force upwards. So now there will be a resultant force upwards, and so therefore the ions are deflected upwards. So that was question number 10 of the magnetic fields homework booklet.